We now start the first module of chapter 6 where we plan to talk about bilinear forms. Bilinear means linear in both the variables. We will see that bilinear maps on a vector space V would be a map from V cross V to the base field F. And bilinear means it's separately linear. That means of the two coordinates, if we fix one, then it is linear in the other. Now, what we plan to study in bilinear forms is that it's a much more generalized structure than the inner product structure on a vector space V. We will first define bilinear forms and then we will define symmetric bilinear forms, and the theorem that we have proved that real symmetric matrices are orthogonally diagonalizable will be used once again. Let F denote a field of characteristic other than 2 and V a vector space over F. When we say that characteristic is not 2, that means 1 and minus 1 are different. We will see that this will be needed when we talk about bilinear forms and symmetric bilinear forms. Definition: a bilinear form F is a map from V cross V to the base field F such that the following properties are satisfied. The first one says f of Ax plus Bx dash comma y is equal to A f of x comma y plus B f of x dash comma y for every x, x dash and y in V and A, B scalars. And the second one says f of x comma cy plus dy dash is equal to C f of x comma y plus D f of x comma y dash for every x, y, y dash in V and scalars C and D. In other words, F is bilinear if it is separately linear in each variable when the other one is kept fixed. This is a standard notation that we use. F of x y is equal to inner product x comma y. But remember that this may not really satisfy all the conditions of an inner product, but we will see that inner products do fall into this category of bilinear maps. Definition: a bilinear form F is said to be symmetric if f of x y equal to f of y x, and it is called skew symmetric if f of x y is equal to minus f of y x. So, here you can see that characteristic other than 2 plays a role, because otherwise we will not have any distinction between symmetric and skew symmetric. Now, an example: the usual inner product on Rn is a symmetric bilinear form on Rn. Another example: let us fix an n cross n matrix with entries from the field F. So, A belongs to M and F. Now, for x y in Fn, define the bilinear form to be inner product x y is equal to x transposed A y. Now, you can see that this is indeed bilinear, that means linear with respect to each variable, and this is a bilinear form on Fn. Now, if F is the real field and if we take A to be the n cross n identity matrix, then this bilinear form is nothing but the usual inner product on Fn. And if, for example, A is this 2 cross 2 symmetric matrix given by 1 comma minus 1 in the first row and minus 1 comma 1 in the second row, then this bilinear form would look like f of x1 x2 comma y1 y2 is equal to x1 x2 times the matrix 1 minus 1 minus 1 1 times the column matrix y1 y2, and then what we obtain is x1 y1 minus x2 y1 minus x1 y2 plus x2 y2. A proposition: let A be an n cross n matrix over F. Aij denotes the ijth entry of A. Then the bilinear form given by inner product xy is equal to x transpose ay is symmetric if and only if A is a symmetric matrix. So, symmetric bilinear forms are given by symmetric matrices if it is of the form x transpose ay. So, suppose that A is symmetric, that means A transpose is equal to A, then y transposed Ax is y transposed Ax transposed, and that is x transposed A transposed y, and that is x transposed Ay. Therefore, inner product xy is the same as inner product yx for every xy in Fn, showing that it is a symmetric bilinear form. And conversely, if we assume symmetry of the bilinear form, that is if inner product xy is inner product yx for every xy in Fn, then inner product ei comma ej is equal to ei transposed A ej, but it is an easy calculation which shows that this is nothing but the ijth entry of A, that is Aij, and inner product ej ei is nothing but Aji. Given that inner product xy is equal to inner product yx for every xy in Fn, we have Aij is equal to Aji for every inj. Therefore, A is a symmetric matrix. Now, let us start with a bilinear form on a finite dimensional vector space V, and let B denote a basis for V, which is given by this set consisting of the vectors V1, V2 and so on up to Vn. Now, given xy in V, we can write x as a linear combination of vi's given by summation xi vi I equal to 1 to n, and y is equal to summation y I vi I equal to 1 to n, such that xi's and yi's are scalars. Now, if we compute this inner product x comma y, then by the bilinearity we obtain inner product summation I equal to 1 to n xi vi comma summation j equal to 1 to n yj vj is equal to the summation over I and j both and xi yj inner product vi vj. If we identify x and y with the tuples x1, x2, xn and y1, y2, yn, after we have chosen the basis B for V, then this expression of inner product xy can be written as x transposed ay. Therefore, this matrix A, whose entries are xij's, is called the matrix of the bilinear form. with respect to a chosen basis B consisting of the vectors v1, v2, vn. And let us use the notations, this box F with respect to B or the inner product with respect to B to represent the matrix A associated with the bilinear form. The following theorem shows how matrices representing a bilinear form with respect to different bases are related. We have learned definitions of bilinear forms and also symmetric bilinear forms. Remember that the characteristic condition on the base field is really important. It should be other than 2. And then we learned a very specific bilinear form given by inner product xy is equal to x transpose ay. And what is interesting is that if we start with a bilinear form, then with respect to a chosen basis that is of the form x transpose ay. So in a sense, this bilinear form x transpose ay is a characterization, and more importantly, the matrix A decides whether the bilinear form is symmetric or not. Now we will see how different matrices with respect to different bases of bilinear forms are related. Theorem: let A and A dash be matrices representing the bilinear form on V with respect to bases B and B dash. We write the basis B as the set consisting of V1, V2 and so on up to Vn, and the basis B dash as the set consisting of W1, W2 and so on up to Wn. Then we claim that A dash is equal to Q A Q transpose for some matrix Q in GLN F. That means it is an n cross n invertible matrix. Proof: if we write the basis as ordered tuples V1, V2, Vn and W1, W2, Wn of Vn, then we can write this B as B dash times P, where P is in GLNF and that is the basis change matrix. Now let V and W be vectors in V, and with respect to chosen basis B, suppose that x and y are the ordered tuples representing V and W respectively. And similarly, let x dash and y dash be ordered tuples representing V and W respectively, and that is with respect to the other basis B dash. Then P being the basis change matrix, we can write x dash is equal to Px and y dash is equal to Py. Therefore, inner product V comma W is equal to x transpose Ay with respect to the basis B, and that is x dash transpose A dash times y dash with respect to the basis B dash, both being the same as inner product V comma W. We have that x transpose Ay is equal to x dash transpose A dash y dash, but we know that x dash is given by Px and y dash is given by Py. Therefore, this expression becomes x transpose P transpose A dash Py. Therefore, the matrix P transpose A dash P is equal to A, and hence if we take Q is equal to P transpose inverse, which is of course the same as P inverse transpose, then A dash is equal to Q A Q transposed, and Q is in GL and F. Now let F1 and F2 be two bilinear forms on V, and let A be a scalar. Let us define these operations F1 plus F2 and A F1 given by F1 plus F2 of xy is F1 xy plus F2 xy, and A F1 of xy is A F1 xy for xy in V, and it is clear that F1 plus F2 and A F1 both are in fact bilinear forms on V. Let us use the notation BV to denote the collection of all bilinear forms on the vector space V. Then, with respect to the addition and scalar multiplication defined above, the set BV is a vector space over F. That's easy to check. And in fact, it is not difficult to prove that if V is a vector space of dimension n over F with an ordered basis B, then the map phi B from the collection of all bilinear forms BV to the set of all n cross n matrices over F, that is M and F, where the definition of the map is phi B of F is equal to the matrix representation of the bilinear form F with respect to the basis B. Definition: a matrix A in M and R is called positive definite if X transpose A X is positive for all X non-zero in Rn. Now a theorem: a real symmetric matrix is positive definite if and only if determinant of AI is positive for all I equal to 1 to n, where AI is the upper left I cross I submatrix of A. This is a very important theorem which characterizes positive definite symmetric matrices, and this is very useful when we try to understand the symmetric bilinear forms. Now this theorem says that let A be in M and R, then the following statements are equivalent. This inner product xy is equal to X transpose AY for xy in Rn represents an inner product on Rn, and statement 2 says A is symmetric and positive definite. So we have already seen that a symmetric bilinear form can be put in the form X transpose AY where A is symmetric, and now when the base field is the field of real numbers and the vector space is Rn, then we see that this bilinear form X transpose AY represents an inner product if we have symmetry and also the positive definite property. Proof: if xy is equal to X transpose AY represents an inner product on Rn, then A is symmetric because inner product has the symmetry over R, and the inner product XX is X transpose AX, and that should be positive for all X non-zero in Rn. Therefore, we have the positive definite property. Conversely, if A is symmetric and positive definite, then this bilinear form xy equal to X transpose AY satisfies all the conditions of an inner product on Rn. Definition: a symmetric bilinear form on a finite dimensional real vector space V is called positive definite if VV inner product is positive for all non-zero vector V in the vector space V. And this is an interesting example of the so called Lorenz form, which is a bilinear form such that VV assumes both positive and negative values, and such forms are called indefinite, and the Lorenz form is one such, which is given by this inner product xy is equal to x1 y1 plus x2 y2 plus x3 y3 minus c square x4 y4, where this capital X is given by this fourth tuple x1 x2 x3 x4, and capital Y is given by this fourth tuple y1 y2 y3 y4. And this is a typical example of an indefinite form on space time R4. Here the coefficient C represents the speed of light and can be normalized to 1, and then the matrix of this Lorenz form with respect to the given basis becomes 1 1 1 minus 1. Now, our aim is to classify all symmetric bilinear forms on finite dimensional real vector spaces. But the main difficulty in this classification is created by the existence of non-zero vectors V such that this inner product VV is equal to 0. For example, in the Lorenz form defined above, this vector V given by 1 0 0 1 is one such. If A is a real symmetric n cross n matrix which is positive definite, then X transposed AY defines an inner product on Rn. So, a symmetric bilinear form is an inner product if it is of the form X transposed AY with A being real symmetric positive definite matrix. That is what we have seen now. Now, what is to be careful about is that we have been using the words bilinear form and inner product interchangeably, but that is only to take care of that notation. Indeed, it is not true that all the symmetric bilinear forms on Rn define inner product. Positive definite condition is absolutely essential. Now it is time that we try to classify them all on finite dimensional inner product spaces. And we have seen the example of Lorenz form where we have some difficulty because of existence of non-zero vectors V and inner product VV is not always non-negative.